Hey everybody, welcome back. Um, Make sure you've already watched my previous video on section 6.1. Um, in section 6.1, the title of the section is the standard normal distribution, but for my first video from this section, I entitled it Uniform because we talked about the uniform distribution, we talked about density curves, finding the area of a rectangle, which shows up in your homework as word problems. And make sure you understand that first. And then we're going to have a separate homework in our class covering part 2, which is really all about the standard normal distribution, no longer the uniform distribution. Okay, so skipping ahead to where we left off on the last video in part 1, which was the uniform distribution, we did rectangles. The standard normal distribution is also a density curve. So the total area underneath this bell-shaped curve is still 1. But obviously, it's more difficult to find the area between two parts of this graph than to find the area of a rectangle, which is just height times width. Okay, so in order to be a standard normal distribution, the standard normal distribution has to be a normal distribution, so it has to have a bell-shaped curve that's symmetric about the middle, and it has to have the parameter of mu equals 0, so the mean equals 0, and sigma equals 1. Remember, sigma is the standard deviation of the population. Just like with the uniform distribution and any other continuous probability distribution, the total area under its density curve is equal to 1, as I've said a bazillion times. The only thing to note here is if you just look at this graph, this is a bell-shaped curve, but notice that it goes off to the left. It goes off forever to the left. So it goes to negative infinity to the left, and to the right it goes to positive infinity. But most of the area is here in the middle. As you can see, there's a lot more meat or area to the graph here in the middle versus out on the edges. It gets so close to the x-axis that the area between that curve and the x-axis gets to be very thin, as you can imagine. Okay, so even though it's harder to find areas underneath a normal distribution curve, as long as it's standard normal, you can use a table, which is very helpful. There are also calculators and software, which I won't be going over because I don't require people in my class to use software or calculator. So I'll just be putting the table that we're going to be referring to in this lecture, and it'll be in this week's module. Okay, so when you have z-scores, which, by the way, standard normal distribution is all about z-scores. When you have mu equals 0 and sigma equals 1, this horizontal axis represents z-scores. So remember, z-scores were those things that we calculated earlier in the book in a previous lecture. Z equals x minus mu over sigma. But fortunately, in this section, section 6.1, all the data values that they give us are already going to be z-scores. So as you can see, a z-score of 0 is right in the middle of the graph. A z-score of 1 would mean that we are 1 standard deviation above the mean. A z-score of negative 1 means that we are 1 standard deviation below the mean, and so forth. But this total area still has to equal 1, because 100% of the time, a data value has to be somewhere in this graph. All right, so like I keep saying, we're able to use a table which is what I'm going to be focusing on. Even though software like computers and calculators can do this as well, I don't require those. So we're just going to learn it the old-fashioned way with the table. So you can find areas. Remember that areas and probabilities are equivalent for different regions under a normal model using table A2 from our book. Calculators and software can give even more accurate results than table A2, but the table is pretty accurate up to 4 decimal places. Sometimes if you do use a calculator or software, you may get slightly different numbers. We'll see an example of that. But when you're doing your homework, quiz, and exam in my course, you can always use table A2, and it will, our software will automatically accept your answer if you're doing it correctly. Okay. So if you are using table A2, which is how I'm going to teach it, it is essential to understand these points. Table A2 is designed only for the standard normal distribution, so z-scores, which is a normal distribution with the requirement that the mean, mu, has to be 0, and the standard deviation, sigma, has to be 1. You can't use table A2 if you have a non-standard normal distribution. But in 6.2, which is going to be my next video that I release, we will be learning about how to convert a non-standard normal distribution into z-scores so that we can use table A2 for those as well. But in this section, we're just going to be working with z-scores. The thing about table A2 is to realize that it's on 2 pages, with the left page for negative z-scores and the right page for positive z-scores. Okay? Each value in the body of the table is a cumulative area from the left up to a vertical boundary above a specific z-score. So we're going to jump into examples of that in this video. But most of the stuff that you need to know is actually in the slides. Okay. All right, so other stuff to be aware of. When working with a graph, avoid confusion between z-scores and areas. Z-score is the distance along the horizontal scale of the standard normal distribution. So you refer to the leftmost column and top row of table A2. Okay, and then remember that area is actually the region under the curve. So for that, you need to refer to the values in the body of table A2. Okay? So the part of the z-score denoting hundredths is found across the top row of table A2. So example is worth 1,000 words. So let's jump into an example. In the slides, we're going to see how to use table A2. Okay, so in this first example, a bone mineral density test can be helpful in identifying the presence or susceptibility to osteoporosis. We're talking about for people here, a disease that causes bones to become more fragile and more likely to break in humans. Okay, so the result of a bone density test, this is true, by the way, this is from the real world, is commonly measured as a z-score. Okay, and quite a few of your homework problems are actually just bone density tests from this section. Okay, the population of z-scores for any z-score is normally distributed with a mean of 0 and a standard deviation of 1. So these test results for a bone density test meet the requirements of a standard normal distribution. Okay, and all of your homework from section 6.1 in this part 2, in your second homework from 6.1, will be a standard normal distribution. Okay, so the graph of the bone density test scores is as shown in the figure. So if they ask us, they say a randomly selected adult undergoes a bone density test, find the probability that this person has a bone density test score less than 1.27. When they say less than, that's the same as the area to the left. of 1.27. Okay. So if you look at the graph, because this is a standard normal distribution, we already know the shape is a bell curve. And we already know that because it's a standard normal distribution, the very middle of the graph is a z-score of 0. And they're asking us to find the probability that a randomly selected person has a bone density test score less than 1.27. So here is z equals 1.27. That's 1.27 standard deviations above the mean. Okay? And because it says less than goes to the left. So the area we're trying to find here is the area to the left of z equals 1.27. So how do we find this green area to the left? Well, in the book they say that the area is just 0.8980, and that's from table A2. So I think for a bit of fun, I'm just going to go ahead and open up table A2. So let me go back to where we were. So it's helpful to just look at table A2. So let me get that real quick. But we can see that this area to the left is what we're trying to look up. And actually the areas in table A2 are all areas to the left. So note that the following are the same because of the aforementioned correspondence between probability and area. Remember, probability and area are equivalent when we're talking about a continuous probability distribution, whether it's uniform or normal. Okay? So let me go ahead and open up table A2 so we can take a look at it here during the video. Okay, so let me zoom in and actually get rid of the camera here. So as you can see here, this is something that you'll be able to download in this week's module if you're in my online course. So it says table A2, and it's a PDF file. And table A2 represents cumulative area from the left, and it's made up of 2 pages. So this page says positive z-scores, and you can see from this picture, it's a little hard to note, but here's our z-score, and then these numbers here in the middle actually represent the area to the left of that z-score. Okay, the cumulative area from the left. And then you can also have negative z-scores. So the other page is for negative z-scores. Well, here our z-score is actually negative, so it would be a number smaller than 0. But these numbers in the body of the table represent this area right here, the area to the left of that z-score. Okay, so let's see if we can go ahead and go back to the slides and figure out how they looked up that area. So they say that the area is 0.8980. So if you look at table A2 and we want to find a bone density test score that is less than 1.27, we just look at the number 1.27. The first 2 digits give us the row, and then the last digit gives us the column. Okay, so here the row would be the first 2 digits, so the row would be 1.2. And then the column would be the last digit. Okay, so here the column would be not just 7, but it would be 0.07. The column is 0.07. All right, so let's look at that table again and see how this works. So row is 1.2, column is 0.07. So obviously 1.2 is a positive number, and that's going to be the row on the left side here. So we're looking for 1.2, which is right here for our row. And then our column is actually on the top. So here our column is 0.07. So let me switch to overlay mode so that you can see this, if it will behave. There we go. Okay, so row is 1.2, column was 0.07. So on the left side, we've got a row of 1.2, which is right here. And then we've got a column of 0.07, which is up here. So where the row and the column meet actually gives us the area that they were referring to. So that's where they got the 0.8980. So the number they gave us, 1.27, because they asked us to just find the area to the left of that z-score, we were literally able to just look up the row and the column, and then this number, 0.8980, represents the actual area or probability of being to the left of that z-score. Okay, so hopefully that's not too bad. That makes sense. And that just represents the shaded area that was shown in the figure. So as long as we're finding a probability that's less than, that's the area to the left. So we literally just look it up in table A2. Okay, that's what we did. Okay, and then so when we found the area, the 0.8980, that was the area that we looked up just now in table A2, and that corresponds to probability. So what that means is if you want to convert it to a percentage, just to understand it better, this is the same as an 89.8% chance that we would have a z-score at 1.27 or smaller. So in the book, they also call it the area below 1.27. Below is the same as less than. Okay, and then less than or equal doesn't make a difference because it's a continuous probability distribution. So even if it were less than or equal to 1.27, because we're talking about an infinitely small sliver, because we have an infinite number of decimals, less than or equal don't make any difference. So it's just the area to the left or the area below. Okay, and because of the correspondence between area and probability, we know that the probability of a z-score below 1.27 is 0.8980 or an 89.8% chance. Okay, so when it is the area to the left, it's incredibly easy to just look it up in table A2 like we did. And in the book, their interpretation of this is the probability of a randomly selected person, human being, the probability that a randomly selected human being has a bone density test result below 1.27 is 89.8% chance. Okay? All right. So then I want to break this down into cases. So let me actually skip to the end of the slides before we do another example. So just for notation, at the end of the slides, I have it broken down into these three cases. The case that we just saw was the easiest case, which is the area to the left, or the probability that a z-score is less than some number. Okay, that's this one right here. So the probability that a z-score is less than some number denotes the probability that the z-score is to the left. So it's the area to the left. That's the case that we just did. So case 1 is the area to the left. We just looked that up. Case 2 is going to be the area to the right. So remember that when we're dealing with inequalities, you may or may not remember this from an algebra course if you've taken those earlier in your life. but less than goes to the left. That's the case we just saw. Greater than goes to the right. To find the area to the right, you're going to have to do 1 minus the area to the left. And that's going to be our second case here. Okay, so let me go to a new example here. It's in the slides for your convenience. Don't forget that you can also download the slides and view them or print them out and write on them if it's helpful. Okay, so using the same bone density test in a new example here, find the probability that a randomly selected person has a result above negative 1.00, which is considered to be in the normal range of bone density readings. So what they're asking us to find here, because it says above, not below, this is the area to the right. So right now I'm going to go ahead and write out all 3 cases, even though we're just starting on the second case. But a lot of people find this helpful, or they have found it helpful when I've been teaching in person. So let me write out the 3 cases. So case 1 would be the case that we just saw an example on, which is the area to the left. So the area to the left is the same as when they're using the word less than. Less than goes to the left. And that's just equal to the area that you look up in the table, in table A2. Okay, so area in table A2. Okay, and for the area to the left, we just have this standard picture where we have a standard normal curve, and then our z-score doesn't have to be negative or positive. It doesn't matter. But what's important is that we're finding the area to the left. So here's our z-score, and then we're finding the area to the left of that z-score. So as long as it's the area to the left or below or less than a z-score, that's just the area in table A2. So you just look it up the way we did. Now the one that we're starting on now is actually the area to the right. So this is the second case that we haven't done yet. Okay, so the second case would be the area to the right. Okay. So in order to calculate an area to the right, because the table is all written as cumulative areas to the left, and the total area is 1, the way we get the area to the right is, well, if the total area is 1, if I do 1 minus this area to the left, that sort of cuts out this part, and it just leaves us with the area to the right. So the area to the right is actually going to be 1 minus the area that we look up the same way we did before in table A2. Remember, A2 is the name for the table we're going to be using. Okay, and then there's one more case after this, which is the area in the middle. But let's return to the example. Okay, so going back to our example here, if we use table A2, we should know, as I just said, that it is designed to apply only to cumulative areas from the left. We find that the cumulative area from the left up to z equals negative 1.00 is 0.1587. But the thing is, we're trying to find this area to the right. So we have to do 1 minus 0.1587. So 0.1587, they looked up in table A2. And then because it's greater than goes to the right. To find the area to the right, we have to do 1 minus 0.1587, which actually gives us an area to the right of 0.8413. Okay. So I've written down the first 2 cases. I do have to erase them so that we can go back and look at the table again. So let me open up the table, table A2. So for this example, they said that z was negative 1.00. So we're still going to look up negative 1.00 as our z-score, the same way we did when it was the area to the left. It's just after we look up that area in the table, we're going to have to do 1 minus that area to get the area to the right. Okay. So let me switch to this mode so we can see it. So for a z-score of negative 1.00, we need to go on the page with negative z-scores. Well, the reason for that is obviously negative 1.00 is a negative number. It has a minus in front of it. And then when we're on the negative z-scores page, once again, our first two digits are going to be our row. So here our first two digits are negative 1.0. And then our last digit is going to be our column. So here, 0.00 is going to be our column. So looking at the left side of the table for the row, negative 1.0 is the row, and then 0.00 is the first column. So where negative 1.0 and 0.00 meet, we get an area of 0.1587. Here, if you're having trouble reading that, let me switch the view to one where we can see the screen more clearly. There we go. So negative 1.0 is our row, 0.00 is our column, so we get an area of 0.1587. Not too bad, but then because it's the area to the right, we have to do 1 minus the 0.1587. And then on a calculator or in our head, 1 minus 0.1587 gives us an area to the right of 0.8413. Okay? So there's about an 84.13% chance that a person who is randomly selected has a z-score that's negative 1.00 or larger. So the area to the right. And then the interpretation that they give of this in the book is because the correspondence between probability and area still holds, we conclude that the probability, which is the same as the area, of randomly selecting someone with a bone density reading above negative 1 is 0.8413, which is the area to the right of z equals negative 1.00. Okay, so that's also equivalent to saying that 84.13% of people have bone density levels above negative 1.00. All right, so it takes a long time to explain, but if you break it down into cases and recognize the case when you're doing your homework, hopefully it won't be too challenging. So we saw the area to the left, which we just look up in the table. We saw the area to the right, which is 1 minus the area in the table. The last case that we haven't seen is the area in the middle. So if I skip ahead again to the notation, what we've done so far is less than goes to the left, greater than goes to the right, that's the area to the right. And then what we're going to work on right now is a z-score between, well, really two z-scores. So here they're calling it A and B. So it's a double inequality. Z's in the middle. But think of A and B as actual z-scores. So I like to call this third case the area in the middle. Okay. So area to the left is case 1. Area to the right is case 2. Area in the middle is case 3. And I've taught this many times, so I've come up with a nice, easy rule to remember, generalized rule. The area corresponding to the region between two z-scores, in other words, the area in the middle, can be found by subtracting, and it has to be the larger area minus the smaller area. Okay, so if we're in case 3, I call it the area in the middle. And you look up each z-score in the table, and then the formula is area in the middle is the larger area minus the smaller area. And the nice thing about that formula is you can just look up the two areas, and then whichever one is the larger number is the larger area, and whichever is the smaller area is what you're subtracting. Okay, so let's see an example of this. Maybe even before I go to the example, I did want to show you what this might look like in the picture. So once again, we're looking at a standard normal curve. Area in the middle is exactly what it sounds like. It's going to be the area between two z-scores. So we might have some z-score here. We could call that z equals a. And then we might have another z-score to the right, somewhere over here. We could call that z equals b. Keep in mind these are going to be numbers. They're not going to be letters like a and b. And then the area in the middle would just represent this part. Okay? And they actually have a nice picture of this on the slides. But basically the reason you do the larger area minus the smaller area is the larger area, for example, in this picture, would be the area from z equals b all the way to the left. And then in order to get the area in the middle, we have to subtract this part right here. And if we subtract this part, that's the smaller area. So larger area minus, we cut out this part, leaves us with this middle area. Okay. So let's go ahead and see that in the example that's on the slides. Okay. So a bone density reading between negative 1.00 and negative 2.50 indicates that the subject, or the person who's doing the test, has osteopenia, which is a medical diagnosis for basically bone loss. Find the probability that a randomly selected subject has a reading between negative 1.00 and negative 2.50. So basically what we're doing here is we're trying to figure out the chance that a randomly selected person has osteopenia, which can indicate bone loss. Okay, so, but what's important here is we're looking for the area in the middle between negative 1.00 and negative 2.50. So what we can do is we can just think of these as z-scores, which is what they are, and then look up each area in the table. And then we're going to, because it's between these two numbers, that's the area in the middle. So we're going to do the larger area minus the smaller area. Okay, so let's see that. Actually, let's actually use the table in this example so we can see it. So our first z-score we've already looked up. So when z equals negative 1.00, we said that that gave us the area to the left was 0.1587. Okay, so when z equals negative 1.00, we already looked that up in the table in the last example. So that area was 0.1587. Okay, and then the one that we still need to look up here would be the area to the left of z equals negative 2.50. And then once we have an area for that, we can decide which one's the larger area and which one's the smaller area, and then subtract. And that will give us our answer. Okay, so let's look up z equals negative 2.50 in the table. So in table A2. So negative 2.50 means our row is going to be negative 2.5 and our column is 0.00. So negative 2.5 and 0.00 gives us an area of 0.0062, as you can see right here. Okay, so 0.0062 is the area. All right, and one of the ways you know it's going to be the area in the middle is when you have two z-scores like this. Also, they usually use the word between. But when you have two z-scores, you look up the two areas, and then you just do larger area minus smaller area. And it should be clear that 0.1587 is larger than 0.0062. So the area in the middle, which is what they're asking for here, is going to be the larger minus the smaller. So that's going to be 0.1587, which is the larger area, minus 0.0062, which is the smaller area. And then if we go ahead and do this, 0.1587 minus 0.0062, that gives us an area in the middle of 0.1525. 0.1525. Okay. All right, and notice the nice thing about subtracting for the area in the middle, as I've already mentioned, is that you can just look up the areas in the table and very clearly one number is larger, and then you just do larger minus smaller. Okay, and then if we go back to the slides, they have those worked out on the book, and I wanted to bring your attention to this slide, which is very helpful. I already described this, but the picture that they have here in the book is very helpful for understanding the area in the middle. So the area to the left of z equals negative 1.00 was the 0.1587. Okay. So that was this one right here. This was the larger area, which was this whole green area to the left. And then the smaller area was the area to the left of z equals negative 2.50. And we got that was 0.0062. So that's this much smaller area here, this little sliver there. Okay. And then in order to get the area in the middle, the reason it's larger area minus smaller area is if you imagine just taking this larger area, but we only want the area in the middle, we have to subtract this smaller sliver on the left side. And when we cut that out, that gives us this picture, which is just the area in the middle, since we've cut out the left side. Okay, so that's why you're subtracting. Cool. And then interpretation. Using the correspondence between probability and area, we conclude that there is a probability of 0.1525 or 15.25% chance that a randomly selected subject has a bone density reading between negative 1.00 and negative 2.50. Another way to interpret this in the real world is to state that about 15.25% of people have osteopenia with bone density readings between negative 1.00 and negative 2.50. Okay. So, one of the cool things about statistics is it's immediately used all the time, especially in medicine and science. Okay, so we saw the three cases, but just to summarize, first case, area to the left, less than goes to the left. You just look it up in the table. Second case, area to the right, greater than goes to the right. That's 1 minus the area in table A2. And then the last case that we just saw is area in the middle, where you have two z-scores, and that's going to be the larger area minus the smaller area, and that gives you the part in the middle. So you just look up each one. So we've seen all three cases, and that completes our video. This is our second video from section 6.1. And then, my next video after this will be 6.2, where we will learn how to actually use the z-score formula to convert normal distributions that are non-standard into a normal distribution. And then once we do that, we can figure out probabilities for a non-standard normal distribution. Just remember in 6.1, all of these problems are standard normal. That's why we're using z-scores. Okay, so as always, thank you for watching. I will see you in my next video.